Hey class! Today we're going to be talking about the bouncy ball problem. Now this problem is a geometric sequence. At least solving for the apex height is. If we're solving for the maximum height traveled by the ball, it is going to be a summation. But right now we're just going to talk about the equation to begin with. As you can see, we drop the ball from a height of 4 feet, which will be our 0th term in this equation. Each time it bounces, it travels 2/3 the previous height. On the first bounce, which will be the first term, it will bounce 2/3 of 4 feet, and continue this equation to the entirety. Here you can see us labeling these axes, the number of bounces on the x and the apex of each bounce on the y. Okay, so now we're going to talk about a geometric sequence and what it means. Now, in this equation, we are going to be working with the explicit formula, which means plugging in any number of bounces, for instance 2 or 3, and we will be solving for the apex height. G of n means the apex height of any particular bounce. G of 0 is our initial drop height. In our previous equation that was 4. And the r is our common ratio, aka the bounce factor. This means however high the ball bounces in terms of its previous bounce. In this case, it would be 2/3. N is the number of bounces. The reason we don't have a -1 after the n is because our 0th term is our max drop height. Alright, so now we're going to be talking about why the bounce factor matters. So, if we drop a bouncier ball, that means that the bounce factor will be greater because the ball goes almost as much as its previous height every time it bounces. But if we drop a not so bouncy ball, that means that the bounce factor will be lower because it is not quite traveling as much as it would if it was bouncing a lot. So the bounce factor is lower. Alright, so now we're going to be looking at an example problem in which the drop height is 4 feet, but the bounce factor is only 0.5 or 1/2. So in this scenario, the ball bounces 50% of its previous height every time. Here's the equation and what it looks like. And now we're going to draw a table so you can understand what kind of values you'll be getting out of here. Again, 0 is our, 0th term, so that's the drop height. So 4 feet is our 0th term. Our first term would be 2. Our second would be 1. Third, 1/2. Fourth, 0.25. Here is another formula which involves dropping the bouncy ball from a height of 72 inches, and it's the bounce factor is 2/3. So every time it bounces 2/3 of the previous height. Here is a data table in which, again, the 0th term is the drop height, 72, and each time it goes 2/3 the previous height. So 48, 32, 21.3 repeating, 14.2 repeating, and 9.4. Here, we're going to be working with another theoretical equation in which the bounce factor is much lower. In this equation, with a not-so-bouncy ball, the drop height will still be 72 inches, but the bounce factor will be 1/10, so much smaller. Here we're going to be drawing the data table, and in this data table, again, the 0th term will be 72, and each subsequent term will be 1/10 the previous term. So 7.2, 0.72, 0.072, and on, until you receive a very, very small number. Alright, now we're going to be talking about summation. Summation is adding up all the terms in a series to find out what they equal. There are two kinds of summation, infinite and finite. You use infinite when working with a series that converges or approaches something but never actually reaches it when it has an asymptote. Solving for the limit of the infinite series, you'd be using this formula, S of n equals g of 1 over 1 minus r. If you do this with the bouncy ball problem, it should come out to equal 0 because the ball almost stops bouncing and reaches a height of 0, but will never actually reach 0. But since we're working with a real-world problem, we're going to be using the finite example. In the finite summation formula, you'll be using the first term multiplied by 1 minus r to the power of n over 1 minus r. If you use this, you'll solve for the what the final term is if you add up all of the previous terms together, what that term shall be. Alright, so now we're just going to be working through an example problem to find the finite sum, or the total vertical distance traveled by the bouncy ball after the set limit of 5 bounces. The reason we chose 5 is just because after 5 bounces it will not be noticeably bouncing, and in a real world problem would just be on the ground. So we set up our equation. Here S of n is the total distance traveled by the bouncy ball, and we start off with our drop height of 4 and the equation 1 minus r, which is 0.5, to the power of 5, because that is the number we chose as our limit. And that's all over 1 minus r, 0.5. This comes out to equal 7.75 feet is the total vertical distance traveled by the bouncy ball after 5 bounces. Well, that's it for the bouncy ball problem. Thanks for watching our tutorial. See ya.